Hello everyone, my name is Simone Clochiatti and I am the ESR2 in the TeraApps project founded by the European Union. My research focuses on the development and characterization of sensitive Terahertz detectors based on the triple barrier resonant tunneling diode semiconductor device. I'm originally from a small city in the northeast of Italy and I pursued my electrical engineering studies between Italy and Denmark. Now I'm carrying out my PhD within the BHE department at the University of Duisburg-Essen in Germany. Let's see first why we need terahertz frequencies. Terahertz refers to a particular region of the electromagnetic spectrum situated between microwaves and infrared light. This type of radiation offers a set of unique physical properties that can be utilized for novel and enhanced applications in the field of communications, radar technology, and imaging. At terahertz frequencies, communications at ultra-high data rates are possible. Applications such as fixed wireless links responsible for home wireless access here could operate above 100 gigabit per second. Terahertz will enable very high-resolution imaging for radar systems. Moreover, many materials are transparent to the terahertz radiation, leading to the possibility of seeing inside some common housing and packaging material for security applications. These technologies can be potentially implemented in the future robotic vision, leading to a new generation of smart robots. The triple barrier resonant tunneling diode is a key component in enabling terahertz operation of an electronic circuit. It's cost-effective, energy-efficient, and can operate at extremely high frequencies. And this is due to its high electron velocity and low capacitive charging time. In our clean room at the BHE department, we grow and process the triple barrier TDs, and we possess the full technology platform for the fabrication of terahertz circuits. This is the Venn diagram of the triple barrier TD. We have three potential barriers and two quantum wells, where the quantum energy levels reside. If a positive bias voltage is applied to the structure, the energy levels in the quantum well gradually align as the voltage is increased. This alignment enables the available electrons in the emitter to tunnel through the structure and result in an electric current through the device. When a negative bias voltage is applied, the energy levels in the quantum wells remain misaligned and no electric current flows through the device. If we now look at the AV characteristic of the triple barrier TD, we can notice that there are three main operating regions. Number one, where the device is reverse biased and no current flows. Number two, where the device is forward biased and a large positive current flows. Number three, when the bias voltage is further increased, the current starts to decrease. We call this region negative differential region, or NDR. Among these three operating regions, we can identify two important ones for terahertz operation. In the region number one, the triple barrier TD can be operated as a detector, so as to receive terahertz signals. In the region number three, the device can be operated as oscillator, so as to generate terahertz power. As we have seen, one of the major advantages of using the triple barrier TD is that we can receive and emit terahertz waves with one device. Here you can see an SEM picture of a processed triple barrier TD, where the anode and the cathode contacts are visible. The device structure lays on top of an indium phosphide substrate, which is a compound semiconductor. The core part of the device forming the triple barrier structure is grown layer by layer on top of the indium phosphide substrate. The active region itself is very thin compared to the device contacts, the collector, and the emitter regions. The wells and the barriers layers are in fact grown with atomic layer precision, and altogether they are only a few tenths of nanometers thick. The complete growth and fabrication of the RTDs is done by our group of PhD students and technicians. Here on the left you can see an example of bow-tie antenna detector with integrated triple barrier TD operating around zero bias. On the right side you can see an RF probe measuring a triple barrier TD. This is part of our on-wafer measurement system, which we use to characterize the diodes in the complete bias range and up to 67 GHz frequency. The on-wafer measurement data is utilized to create an accurate equivalent circuit model of the triple bar RTD. The model is in fact a very useful tool to estimate the performance of the device at very high frequency, and also to design Terahertz circuits, such as detectors and oscillators. In this picture you can see the quasi-optical measurement setup, which is used to characterize the detectors in the free space. The setup consists of a Terahertz power source at some distance with respect to our Terahertz detector, which we intend to measure. The Terahertz power is then sent to the free space and is collected by the Terahertz detector. The detector response is measured through a lock-in amplifier at the antenna arms, and finally displayed in form of responsivity versus frequency, as you can see in the plot. My future work will continue to focus on the detector characterization and on the design of an on-wafer calibration kit for triple barrier RTD measurements up to 500 GHz. Thanks for your attention, and I hope you enjoyed this video.